For our next molecule, we have an ion. It's called aluminum tetrachloride. And why would aluminum tetrachloride be an ion in the first place? Well, aluminum only has 3 valence electrons. So if it's going to form bonds with 4 chlorines, chlorines has 7 valence electrons, so they're looking for single bonds to come up with that 8 valence electron. You probably need an additional electron to accomplish that. Let's find out by drawing the Lewis structure and see what we get. Aluminum is going to go in the middle. It's the lowest electronegativity out of aluminum and chlorine, so it's a central atom. So let's put aluminum right here. And we'll have 4 chlorine atoms like this. And they also will form a single bond, like so. Now remember, aluminum only has 3 valence electrons, so to come up with a 4th electron to make the bond, it's going to need 1 additional electron, so it's going to become an ion. So that's what that looks like. Of course, each of the chlorines will have 3 free electron pairs. So now remember, even though it did gain an extra electron, aluminum has no free electron pairs, just 4 sets of 2 electrons making bonds with chlorine, and so therefore it has no free electrons. So the VS-EPR structure notation will look like that. 1 central atom and 4 atoms on the outside. So this looks like it's going to be a tetrahedron. It's going to be a tetrahedron shape, aluminum in the middle, and the chlorine atoms want to be as far away from one another as possible. So the only way to accomplish that is if the atoms would form into a plane, the angle between them would only be 90 degrees. That's not enough, so they can reform the shape in such a way that you end up with an aluminum at the very center. You end up with 3 chlorines out like this, and 1 chlorine at the very top, like that. So if you draw the lines connecting these and connecting those like that, and you can see right here you have kind of like a 3-sided pyramid, and then we have aluminum in the middle of the pyramid, and you have the base that forms the 4th side, so that's where the name comes from, tetrahedral molecule or tetrahedron. So that would be the shape of that. And it's, of course, not a molecule per se, it's an ion molecule. So tetrahedron would be the shape. Okay, 4 appendages, 4-sided pyramid, well, 3-sided pyramid with a base in a way, and so that's the shape of that particular molecule. That's how you do that.
This is Dr. B. Let's do the SOCl2 Lewis structure. Sulfur has 6 valence electrons, oxygen has 6, chlorine has 7, we have 2 chlorines, and that equals 26 valence electrons. Sulfur is the least electronegative. You can go at the center. Let's put a chlorine on either side, and then the oxygen right there. We have 26 valence electrons. We'll put 2 electrons between each of the atoms, form chemical bonds. There's 6, and then around the outside, 8 and 26. At this point, you might think you're done. Everything has 8 valence electrons. You've used only the 26 that you were given. Looks like a pretty good structure. The problem is we really need to check the formal charges. Sulfur is in period 3, and that means it can hold more than 8 valence electrons. So let's check the formal charges for SOCl2 just to be sure. Okay, so let's look at the chlorine. Chlorine is in group 7 or 17 in the periodic table, so it has 7 valence electrons. Non-bonding, these electrons right here are not involved in chemical bonds. There are 6 of them. And then we have 2 forming the bond with the sulfur, and we'll divide that by 2. 7 minus 6 minus 1 is 0. Because the chlorines are symmetrical, they'll both be 0. For the sulfur, 6 on the periodic table, we have 2 non-bonding, and then we have a total of 6 involved in chemical bonds, and we'll divide that 6 by 2. 6 minus 2 minus 3 is plus 1. Finally, for the oxygen, in group 6, 6 valence electrons, we have 6 not involved in chemical bonds, 2 bonding, which we divide by 2. 6 minus 6 minus 1 is minus 1. So when I look at this structure in the formal charges, I see I have a plus 1, minus 1, this might not be the best structure. I should probably investigate another structure. And because I see a +1, I think there's probably going to be a double bond in the next structure I'll try. Chlorines don't really form double bonds. I'm thinking it might be on the oxygen. So let's try that, see what it looks like. So I've moved the 2 electrons that were up here to right here to form a double bond. Still have the same number of valence electrons in the entire molecule. Let's check our formal charges for chlorine. Really nothing's changed with chlorine. We have 7 valence electrons minus the 6 here that are non-bonding and the 2 that are bonding. So it's still 0. For sulfur, 6 valence electrons, 2 non-bonding, and now we have 4 plus 2, 6, 8. 8 total bonding divided by 2. 6 minus 2 minus 4 is 0. And then for oxygen, 6 minus the 4 non-bonding, we have 4 bonding here divided by 2, also equals 0. Because my formal charges are all 0 now, I know that this is the best structure for SOCl2. So when you're drawing the Lewis structure for SO Lewis structure, we have a total of 16 valence electrons for HOCN. Hydrogen always goes on the outside of Lewis structures, and when we look at the oxygen, nitrogen, and carbon, carbon's going to be the least electronegative. So let's put that in the center. We'll put a nitrogen over here, an O, and then right here we'll put the H. In this case, I pretty much followed the way the structure was written above. But it does make sense. Carbon's the least electronegative. It should be in the center, and hydrogens are always on the outside. We'll take and put 2 valence electrons between atoms to form chemical bonds. We've used 6 valence electrons. Complete the octet for nitrogen. 8, 10, 12. Let's go back to the oxygen. 14 and 16. So we've used all our valence electron. At this point, the hydrogen has 2. The oxygen and the nitrogen, they both have 8. But the carbon here in the center only has 4. So we're going to have to share valence electrons. Since nitrogen is least electronegative here, I think I'll take 2 from the nitrogen and share them with the carbon to form a double bond. So the nitrogen still has 8 valence electrons, but now the carbon has 6. So let's take another 2 from the nitrogen and share them with the carbon to form a triple bond. Nitrogen still has 8. We're still using the 16 valence electrons we have for the HOCN Lewis structure, but now the carbon has 8 as well. So we've completed the octets on all of the atoms. If we take a look at our formal charges, we'll find that there's 0 for each atom in this Lewis structure. If we were to take and use a triple bond between the oxygen and the carbon, we wouldn't have formal charges of 0. That would mean that it's a less likely Lewis structure. So this is the best Lewis structure for HOCN. This is Dr. B, and thank you. Nitrogen is in group 5 or 15 on the periodic table, 5 valence electrons, but we have 2 of them. Hydrogen's in group 1, it has 1 valence electron, again we have 2 hydrogens. So 10 plus 2, a total of 12 valence electrons. Hydrogens always go on the outside, so let's put the 2 nitrogens in the middle, and then we can just put a hydrogen on the outside of each of those. So we've used the 2 hydrogens and the 2 nitrogens. We have 12 total valence electrons to work with. We'll put a pair between the nitrogen and the hydrogen to form a chemical bond over here, and then in the center. So we've used 2, 4, 6, and hydrogens only need 2 valence electrons for a full outer shell. So we've actually filled the outer shell of both the hydrogen. So we won't put any more there. So let's go to the center atoms, the nitrogens. So we have 2, 4, 6, 8, 10, and 12. So we've used all 12 valence electrons. At this point, this nitrogen has an octet, but this nitrogen right here only has 6 valence electrons, so it needs 2 more. What we can do is take these 2 valence electrons here and move them to the center to form a double bond. So we're still using 12 total valence electrons, but now this nitrogen, it has 8, and this nitrogen has 8. So we've used all 12 valence electrons that we started with, and everything has full outer shells. So this is the Lewis structure for N2H2, and this is Dr. B. Thanks for watching. Be a pro at drawing the basic Lewis structures. There really are only 5 main steps that you need to know. Let's get started. Step 1. Find the total number of valence electrons for the molecule you're drawing the Lewis structure for. Let's try one. We'll use the periodic table to figure out how many valence electrons each element has. Hydrogen is in group 1 on the periodic table, so it has 1 valence electron, but the subscript tells us that we have 2 hydrogens. So we'll need to multiply that by 2. Oxygen is in group 6 or 16. It has 6 valence electrons, and when we add that up, 2 plus 6, we get a total of 8 valence electrons for H2O. Remember, valence electrons are the outer shell electrons. They're the ones that form chemical bonds and interact with the world around them. Let's try one more, cyanide. For cyanide, we can our Lewis structure. For CH3Br, there are a total of 14 valence electrons. Hydrogen always goes on the outside, and since carbon is less electronegative than bromine, we'll put the carbon in the center and the bromine on top. We have 14 valence electrons for the CH3Br Lewis structure. We'll put 2 between atoms to form chemical bonds. We've used 8, and then around the bromine, 10, 12, and 14 valence electrons. So we've used all 14 valence electrons. The hydrogens each have 2. The bromine has 8, and the carbon has 8 as well. So the outer shells are full on all the atoms in CH3Br. So that's it. This is the Lewis structure. Hi, this is Dr. B. Let's draw the acetic acid Lewis structure. The key to drawing this structure is to realize that this COOH right here is what we call a functional group. It's actually a pretty common functional group in organic chemistry. So whenever you see COOH, you know it's going to look like this right here. We can attach that then to this rest of this up here, this CH3. So I'll put the C right here and the H's around it. In the acetic acid Lewis structure, we have 24 valence electrons. Let's count and make sure we've used them all. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've used all the valence electrons, and we've used all of these elements up here to make our acetic acid Lewis structure. This is Dr. B. And thanks. This is Dr. B. Let's do the Lewis structure for H2O2 hydrogen peroxide, also called dihydrogen dioxide. On the periodic table, hydrogen's in group 1, so it has 1 valence electron, but we have 2 of them, so we need to multiply by 2. Oxygen group 6 or 16, we have 2 of those, so let's multiply that by 2 as well, for a total of 14 valence electrons. Let's draw it. We'll put the H's on the outside. They always go on the outside. So O, O, and then an H, and an H here. And let's put some valence electrons there. First, we'll form the chemical bonds. 2, 4, 6 valence electrons. Hydrogen only needs 2 valence electrons for a full outer shell, so it's good. And now we'll put electrons on the inner atoms. So we have 2, 4, 6, 8, 10, 12, 14 valence electrons. We've used all our valence electrons, and you can see that each oxygen has 8 valence electrons. So it has its octet satisfied. The hydrogens are good. That's the Lewis dot structure for H2O2. We can draw it also as a structural formula, and that would look like this right here. That's it. Lewis structure, H2O2. This is Dr. B. Thanks for watching.